Okay, good afternoon. Any questions? Comments on the midterm?
It was really hard.
Come on. You should have taken my course previously.
Are you going to post solutions to the midterm?
Yeah, they'll be on Gradescope. So when we release this course, I was surprised at how many of you got stumped by the 1.6 thing. It's 16 over 10, right? And we know how to divide by powers of 2 and multiply. So anyway, so we are still grading, so find out how. So next Tuesday, we'll actually have a Verilog tutorial. Verilog is the hardware description language, which is pretty much used in the. Actually, before that, were there any other questions? Okay. So Verilog is the kind of the hardware programming language, which is the dominant one in the industry. So this year I decided to give you guys an exposure to that. So, and in the process, our final design assignment, not the coming one, but the one after that, would the optional one would be based around a Verilog design where you kind of do things onto hardware, but that's an optional one, so you have to kind of decide whether you want to do it or not. But in any case, on Tuesday, the Verilog introduction would be done by Salma, who is one of our TAs. And then the latter half of the lecture would be done by a senior student of mine, Paul Martin, who's going to then show you how to take the Verilog design and map it onto an FPGA board. FPGAs are these special kind of chips where essentially you can send them a netlist of gates, and they have lots of gates and lots of wires, and you basically send them a description on to which gates and how to wire them. So essentially, think of them as programmable hardware. So he'll show you a couple of simple examples. Also, then some things that would be important for the design assignment. And the design assignment is going to be basically you have to create or mimic kind of like a combination lock, kind of like what you see in safes in hotels, the safety box in hotel rooms, okay, or some of the modern digital locks. So essentially, some key sequence with which the lock can open and close, and an ability to program a new sequence. Okay, so that's kind of the idea. So we'll hand out to you a little FPGA board and a little matrix keypad, which is basically a keypad which is a thin membrane, and it looks like a telephone keypad, and hooks up to the FPGA board, and the FPGA board has some LEDs, and also you can connect to the FPGA board onto your laptop. So there will be two elements to it. Type on the keyboard and mimic a lock, locking and unlocking action, except that we don't have a real lock, so that would be through an LED. So you'll light up an LED to indicate the status of the lock. And then also as you type in the code, you'll have to send the code that you typed in over the USB onto your laptop, into a program running on your laptop. Now, to make this thing happen, the part which is that you'll have to install some software on the laptop. Informally, I asked the TAs, and it seems like there are more Macs than Windows. This assignment, you'll do it in pairs. So we have 58 students, so if anyone who wants to do it, you'll have to find your own partner. We'll not get into that game. We'll basically open up a Google form where you'll have to indicate to us who your partner is, and then we are going to give you a unique code for your lock. Okay, so and that code could be 4 or 5 or 6 digits. So your designs would all be different that way. And the reason I brought up the Mac part was that these tools that we are using are directly installable on Macs and on Linux machines, but not on Windows. So if you have a Windows laptop, it would be great if you team up with someone with a Mac. If not, it's not end of the world. We are going to hand out a virtual machine. Anyone knows what virtual machines are? Okay. So these are basically simulate another computer on your computer. Okay. So there is a free package from Oracle called Virtual Box, which can then run a virtual machine on your laptop. So that works with Windows. So we are going to hand out to you a virtual machine with an installation of Linux on it with all the tools. And then you install it on your Windows. So you'll need 16 gigabytes free on your 16 gigabytes of disk space free on your laptop, and your laptop should be reasonably powerful. Okay, probably 8 gig type RAM or something like that. So if you don't have a machine of that capacity, then make sure your partner does. Okay, I guess that's short. And Paul will hand out more detailed instructions and all as we do that. On Macs, we'll hand out the instructions so that you can directly install. If you happen to have a Linux machine, that will also work. It cannot be a machine which you do not have access to install programs, because you have to plug in that FPGA board. So it has to be a laptop or a desktop at home, not a server or something like that. Let's see, what else? So we'll hand out all those instructions. If you are not comfortable with Unix type, sort of command line type stuff, then again, make sure your partner does, because unfortunately these tools are not friendly GUI type tools. You have to type stuff in and also. But that's how the EDA tools are. It's nothing. That's how. So as you move into more engineering and technical software, you have to be comfortable with that. So we'll hand out all the details to the extent we can, and we'll obviously help out on Piazza. But again, it's an optional thing, so you don't have to do it. But I think it should be fun. We have done it ourselves. That's what Paul has been doing the past week or so. So I think we have the obvious wrinkles worked out. But I'm sure there'll probably be issues when it comes to installation. The virtual machine route is the safe route, but you have to download a huge file, and also your machine should be up to snuff in that case. Let's see. And then what you have to do is you have to submit a video onto YouTube of your lock working, showing its various functions. Because we kind of figured that having everyone visit us in the lab and showing us would be rather painful. So you submit the design and you submit a video of your lock working different functions and all. Just take it with your phone and upload it, and then submit the URL for that. So, and oh yeah, one final thing: if you don't return the hardware, then you won't get the grade. So you have to return the hardware before the finals. It's an optional one, so the way it works is the following: the submission date will be before the finals. So you'll have to make a choice, but you cannot make that choice knowing your grade on this design assignment. So if you submit, you will be graded on the design assignment. If you don't, then not. Okay. So Tuesday, that's basically what's going to happen. Happening since the nature of Tuesdays, I think it's partly show and tell with the real board and all. Don't miss the lecture, and if you are interested in doing the final design assignment, because unlike my regular lectures where we are able to record everything, that will probably not work out very well for Tuesdays. So be here in person. Also, that will also give you a chance to talk to Paul, become familiar with him, because he kind of acts as a extra TA for that portion. He was a TA in this course last year, so he's kind of very familiar with the content. So what else? Hopefully tomorrow or day after, there will be a P-set and a design assignment coming out. This one's still based on Logisim. The P-set would be shorter than P-set 2, which I know was very long. And then there's going to be one more P-set after that. So this P-set is going to be on finite state machines and Datapath. So that's the set of things. Any questions? Okay. If not, so last time around, I think more than a week ago now, I had begun to cover kind of this other style of digital sequential systems, namely those which we think in terms of data and data being manipulated, and I was calling them as data path. And the style was, and the last example I had covered was this one of a shift, bi-directional shift register. But kind of the main point was that instead of thinking in terms of states and we are jumping between states, here there are too many states. We are dealing with n-bit data entities. So we kind of think of it as in terms of our usual software programs. So usually you would be given some sort of specification in terms of some signals, and some of those signals are going to be data-like signals, n bits. Some of them are going to be control-like signals, smaller number of bits, or even a single bit. And in this particular example, what we had was we wanted to create this register which has the following functionality, that if the reset signal is high, then we reset out to 0. If the left signal is high, then so basically we have a register and we shift that register to the left, and I have an input called SIN, standing for serial in, and that fills into the LSB. So the contents of the register are moved to the left. That opens up a space on the least significant bit. So whatever was in the serial input, we put it there, that one bit. And right is the other way around. We shift right, and serial in, that one bit goes into the MSB, which is now free, and otherwise out is unchanged. So basically, what in terms of program logic, it then looks like if reset, next state is 0. So we think of that register as a state register. If reset is low and left is high, then next state is, and this syntax basically is saying that the new contents of the state register are whatever were the old content of the state register, but the lower n-1 bits, now they are sitting in the upper n-1 bits. So we kind of shifted left. And then in the least significant bit, we put SIN, which is a 1-bit entity. And likewise, if it's not reset and not left, but it is right, we kind of do it the other way around. And otherwise, oh yeah, I forgot the load. So if there is a load, then we just load in, which is a n-bit entity, onto the register. And then in the otherwise case, we leave it unchanged. And out is state. So basically, I have n-bit quantities, which are in and out. I have a 1-bit quantity, which is SIN, and then I have these control signals which are telling what to do. And then when it came to implementing it, the style is something that we saw in other examples also, which is we think in terms of the state register, and then the multiplexers get to decide what is the next value we are going to feed into that. So in this particular case, there were a bunch of choices if you look at the program state. So there are 5 possible options. So we essentially have a multiplexer with 5 inputs covering the 5 cases. One case, which is the uppermost one, is just taking the current state and feeding it back, and that's number 4. The next choice, number 3, is we take the external world input in, which is some n-bit quantity, and feeding that out here. Then I have 2 choices, shift left and shift right, and that, as we had discussed before the midterm, is basically a wiring option. So we just kind of wire appropriately, and SIN, which is a 1-bit quantity coming from outside, feeds into LSB or MSB in out here. And then the final choice is we load 0, that's a reset. And then typical of this design, the control of the multiplexer is the output of some combinational logic that you have to design, which in turn depends upon all the other signals that you have. So in this particular case, this combinational logic is generating the select signals, and input to this combinational logic are all the control signals I have: reset, left, right, load, and you'll have to figure out what combination results in which input of the mux be done. So this style of creating the hardware is, again, all the examples that we saw had that as a common theme to it. So you create this schematic, and yeah, this is a pointer. Just remember these are wires. So that pattern that we saw in the counter examples in timer and So what that leads to is kind of a more general, uh, more more general view of what sequential systems are. So it is true that all sequential systems, ones which we can implement, are finite state machines. And if we so wished, we could always write them in terms of that state chart with arrows going all over. But as we also realize is that if we have these quantities which have large number of bits, like a 32-bit register or 64-bit register, and potentially many of them, then writing them explicitly in terms of states is basically out of the question. We have too many states. So what we now begin to do is we begin to think of our sequential system that some parts of it are better expressed in terms of how the data is being manipulated. And that's where kind of the program style comes in. And perhaps other parts of the system would be better expressed in terms of what control actions are happening. How, like I'm trying to detect a pattern or look for a rising edge or things like that. So a general view of then sequential systems is to think of that there is a data-oriented part and there's a control-oriented part. Remember, both of them are finite state machines. It's just we think and implement them somewhat differently. Okay, so in general, then sequential system could be thought in terms of a data path and a controller. Controller is one which we implement using the techniques we did first, namely a state diagram and things like that. It will usually have a small number of states, which basically means it will not be dealing with n-bit chunks. It will be dealing with signals which are single-bit signals or maybe a couple of bits, 3 bits, something like that, not n-bit stuff. Okay, and then I'll have the data part, which is referred to as data path, and that is where we are going to be primarily manipulating n-bit entities, but under the control of signals which are 1-bit signals. Okay, so what you see in this diagram are these two parts. The upper part is the control FSM and the lower part is the data path. In the data path, I have shown some adder, multiplexer and all. They are kind of besides the point. The main thing is that these are things which manipulate n-bit things, 32 bits, 64 bits, some large number of bits. Whereas the FSM, control FSM sitting up there, is few states, maybe tens of states, at best hundreds of states, not more. But it is orchestrating what the data path is doing. It's like the traffic cop, whereas the data path represents the road and kind of the operations that are happening on it. Now, it's not as if these things are mutually decoupled. They talk to each other. So the controller sends signals to the data path telling it what to do. They are the commands. You can think of them in a computer term. These are the instructions telling the data path what to do. And then there are signals which are going back up from the data path, which are the status signals out here. This is the data path telling the controller what happened. Like, was there an overflow? Was the result a 0? Those kind of things. Okay, so these are sort of command signals and status signals. What about the outside world? Things which are n-bit stuff, the data type things, they will come or go out of the data path. So this is n-bit, this is n-bit. So these are our data-like signals, but they will be accompanied by other signals which are external world's way of telling our system what is happening. And those would be the control inputs which are coming from the external world or outputs which are going out to the external world. So to give you an example, it could be that the external world has a signal saying, hey, there is data for you. So I'll have the 32-bit data, let's say, and I will have a signal which goes up whenever there is valid data on those 32-bit lines. So that other signal which is saying there is actual 32-bit data present on those lines is the one which would so one is data, the other is control. Usually there are a whole bunch of other signals that would be there. It could be that when our system is done processing the data, it will raise a signal saying, I now have valid output for you to read. Okay, so there would be some sort of an acknowledgement coming out. So usually the systems would specify these kind of things. To give you another example, and you'll face that both in the design assignment number 3 and 4, our view of finite state machines thus far had been a little bit idealized. So we always thought of something was happening at every clock tick, a new input arriving every clock tick. In reality, clocks are very fast, hundreds of megahertz, gigahertz. On the other hand, inputs like, let's say I press a key, they are at a very different scale. Like when I press a key, it's probably a fraction of a second, 10 millisecond, 100 millisecond, okay. But each press of the key that I may do on the keyboard, that corresponds to, if you just think about it, my clock is nanoseconds, my key presses are milliseconds, you're looking at 6 order of magnitude, so I can have millions of clock cycles in a single key press. So now think from a state machine perspective. What's happening is each time I press the key, it's not as if you are seeing that key press just for one clock tick. You are actually going to be seeing for a whole bunch of clock ticks. So usually you will have to do some additional things. For example, it could be, depending upon the keyboard, it may say normally all the wires coming out of the keyboard are high, and whenever the key is pressed, it goes low. Let's say a very simple keyboard. For every key, there is a wire coming out. So if I have 100 keys, there are 100 wires coming out. But those wires by default are high. When the user presses a key, the wire goes low. What your design, the circuit will have to do is to look at these wires, and whenever it sees something went low, it has to keep sampling it, and until it sees that it went back up again. Because the key press itself may take, as I made the case, millions of clock cycles. So real FSMs have to deal with these issues that timing of the outside world may be very different than timing of your internal thing. Your clock speed can be very high. So, these signals which are coming from outside worlds, physical, mechanical signals, they may change very slowly, and you'll have to design your state machine to account for that. Okay, when you see a key being pressed, then you may have to go into a state saying, okay, key has been pressed. Let me wait for the key to be released. And you'll keep spinning there, and then when the key is released, you'll come out and then say, aha, the letter K was pressed. So Paul will give some examples of that through Verilog design process as well, but you'll have to think in sort of these terms. So real systems then have these two components: controller, data path. Data path is where you do processing, add, multiply, all those kind of stuff, typical operations. Controller is where you do things like, if something happens, then do something else, what operation is to be done next, all those kind of things will take place. So the kind of design that you would have to do in the next design assignment, which is individual mandatory design assignment, would involve you to make a data path and then control it using a simple state machine. So that's what a simple controller FSM. So what I will do now is to go through, and yeah, I already said all of this. So I'm going to show you an example system. This is from the book of how some digital system may have both these elements. Okay, and what we have out here is an example of a vending machine. So vending machines where we put in coins and then we press a button to fetch some object into the vending machine, and usually kind of you have to put in coins until you have deposited sufficient amount of money, and then once there is sufficient money, some sort of a mechanical gizmo goes and releases the drink or water bottle or whatever it may be. So it's in that vein. So we are going to be designing this vending machine controller. Our spec is the following. So our machine has to receive coins. It can receive 3 kinds of coins: nickel, dime, and quarter. And then it will accumulate the sum, like how much money the user has deposited. And then there is a dispense button. So the user deposits coins, presses the dispense button. If sufficient money was deposited, then the drink is released. If the sufficient money is not deposited, then the drink is not released, and this machine has only one kind of drink. And if sufficient money was deposited and the drink is released, then if there is any extra change left over, that is returned to the user. So there is again some mechanism through which the coins are released, nickel, 1 nickel at a time. So this is an example where, as you can see, I'm dealing with money. I'll have to worry about how much money has been deposited. I'll have to count them. I have to subtract those kind of things. They snack of data. So this data part. If you think about, like, if you were to keep track of all of that in a state diagram, it would be pretty painful. Okay, I mean, you'll be counting and things like that. It would be pretty painful. On the other hand, in this example, there are also things about sequencing, right? Release nickel at a time. Release the drink, okay, when enough money has been deposited. Those kind of things, and they are best thought in terms of our state diagrams. So we'll see shortly that if we design things this way, that sort of sequencing type operations we put into the controller FSM, whereas data manipulation kind of operations we will put into the data path. This partitioning is not rigid. Probably the only statement I can make is that if I have lots of bits, that certainly smacks of data path. But if I have sequencing operations, a lot of times you can also do it within the data path. At that stage depends whether you are which way you go. More complicated control, lots of branches, for loops, those kind of things, then you definitely need a controller represent. But simple sequencing can often be done within the data path, and as you design these things, you'll yourself kind of realize for a given problem what works best. So the way to start out on problems like these typically is to think of a data path which is capable of doing whatever operation you want. Okay, if I needed to add stuff, if I needed to release a bottle, it somehow has some way of doing all of that. Okay, in our case, it will be a data path which is going to keep track of money, and it's going to tell me when there is sufficient money, those kind of things. So you start out by saying, I have a data path, and now let's think in terms of what sequence of operation I need to do. So in a sense, think about your controller first. So in this particular case, I have created, or rather the book chapter had this controller, and there are some very distinct states. So there is a state where we reach after the initial reset. So this is our start state. Okay. So if we were to show it in our usual manner, this is the start state. Okay. So we start in the that state, and now the thing is, we have to wait for money to be deposited. So this is the state where the user deposits money. We are waiting there. The user feeds in coins, and then at some stage there is going to be enough money deposited. And now imagine somehow our data path sends us a signal saying there is enough money. Okay, so we'll keep track of the money in our data path. Every time the coin is deposited, some register in the data path is incremented. So we don't handle that out here because that would be a large number of states. So it's part of data path. So when there is enough money and the dispense signal was pressed, the dispense button was pressed, then we move to a state called serve 1. So two conditions have to be met. There is enough money and the dispense button is pressed. Otherwise, we stay put into the deposit state. When we are in serve 1 state, then what would happen is that somehow we'll be activating some mechanical gizmo which will release the bottle. But that process will take time. So we'll assume that that mechanical gizmo has some sort of a signal coming out of it which tells us that it has done dispensing the bottle of drink. So we're going to assume there is some signal called done. So when the dispensing is done, then we move to a state called serve 2. And we are going to wait there until done goes back to 0. So done is some sort of a pulse. Once done goes back to 0, then I have two possibilities. One is the user gave excess money, and the other is the user did not give excess money. So what would happen is if the leftover change is 0, so 0 is some sort of signal coming from our data path saying the leftover money is 0, then we are going to go back to the deposit state. If on the other hand, the leftover money is not 0, so then we are going to take this other direction, and now we have to dispense the change. And what we'll do is, so if you recall, we selected the coin sizes to be 5, 10, and 25. So any excess change which is left over is going to be a multiple of 5. And we are going to just return nickels and assume that the machine has a large supply of nickels. So what we'll do is there's some other mechanical entity to which we are going to send a signal saying release a nickel, release a nickel, release a nickel, and we'll keep doing it until the excess drops down to 0. So these two sets of states are doing that. So what we are doing is we are going to be releasing change out here until we are down to 0. And then we are going to go back to the default state. So that's the high level design. There are lots of details we are glossing over, and we are making all these assumptions about there is some mechanical gizmo, there is some stuff coming out of the data path. All those things we have sort of glossed over, but at a high level this makes sense. Now, how to come from a problem description to this one? Practice. There is no other easy way because it's so very problem specific, and your design might be different from someone else's. So, you have to just ponder about the problem and kind of think about how you would do it. Not all that different from if you were to be writing a piece of software for doing it. I mean, at this level, you are basically thinking about your algorithm, what your high-level flow of sequence of actions is. Any questions on this thus far? Okay, so once we have this high-level stuff, we are going to now assume that it exists, and now figure out what our data path has to do. So there are certain assumptions we made about the data path. So let's talk through that, and in the process, we are also going to begin to lay down what signals we are dealing with. So that stuff I had on the previous slide, that was a high-level description of the controller. This controller, we again assumed a whole bunch of signals, so let's start fleshing them out. We are going to have signals indicating what type of coin was deposited. So every time the nickel is deposited, the nickel goes high. Every time dime is deposited, a dime signal goes high. And also there are these signals indicating type of coins. There is the signal which is a dispense button. So the user presses the dispense button, the signal goes high. There is the reset, with kind of starting out thing, and then we had assumed this done signal, which is coming from external mechanical part of the vending machine. Okay, so we are going to tell the mechanical part of the machine to take some action, and when it's done, it's going to assert it. So this is coming from the mechanic. From mechanical part of the machine. Okay. And then we have our data path. So this data path, it has to take certain actions. So now you have to think in terms of what operations we have to do. So one thing we know is we have to keep count of money. So there's going to be some register in which we are going to keep track of how much money is there. So that register is this guy. So it's an n-bit register where we'll keep track of money, and it's sufficiently large so that anything reasonable a user can deposit, we can keep track of. Now, if you think about it, what are the kind of operations we have to do? Well, first thing is we need to be able to reset it to 0. So that's out here, this option. Second thing is we need to keep the value the way it is. If the user is not doing anything, nothing is happening, then every clock tick the value will remain unchanged. So that is this part. And then the next thing that we have to do is there are kind of really two operations that we would need to do. One is we have to add coins being deposited, and the other is we have to subtract the price of the drink being dispensed. So I have to add and subtract, and my choices of operands in case of add are 5, 10, and 25, and in case of subtract are the price. And then also one final thing, when we are subtracting, as we release the nickels, we also have to subtract the nickel. So there are 4 possible values of operands: price, 1 nickel, 2 nickel, and 5 nickels. So instead of doing 5, 10, and 25, we just count in terms of nickels. So 1, 2, and 5, and the price. So this is nickel, this is dime, and this is quarter. So I have a mux which lets me select what value in terms of how many nickels, and then I have this piece of hardware which lets me do add or subtract. So what this has now done is it basically says that, look, I'm going to need a bit coming out of my controller saying whether to do add or subtract in a given cycle. I'll have some more bits, 4 bits, coming out telling me which input of this multiplex to select, that is what operand. I'll have another bit which is going to be, 3 bits which are going to be coming out here, which are going to tell me what to do. Maintain the current value, set it to 0, or do this add subtract business. So collectively, these 8 signals are going to let me control on each clock tick how the amount is going to change. Any questions on this, like what's going on? So we are basically at this stage kind of doing a free form design. We're thinking, what kind of operations do we need? I need to add money, I need to subtract money, I need to hold the value of money, I need to set it to 0. So we basically just structured like this. There could be other ways of designing it, but this is a reasonable way of thinking about it. Any questions on this? Okay. Can someone suggest an alternative design? How you might approach it? For example, let's say, could you do it with a single mux? Well, answer is you can do whatever permutations you want. It's just that how many resources you will need. So if, for example, let's say I want to do it with a single mux, then what are my options? Retain the value, make it 0, add 5, add 10, add 1, add 2, add 5. So I can have 3 separate pieces of logic, an adder dedicated to this adding 1, adder just dedicated to adding 2, adder just dedicated to adding 5. Subtract the price. Now I don't know the price, so I will need a subtractor. And that would be it. So I can sort of create other ways of structuring this logic. There's nothing wrong about it. It's just that it will probably be costlier because it will need multiple adders. But other than that, it will work out fine. So in this step, what really we have to do is we have to think in terms of what operations I need to do on my state. And I put sufficient hardware to be able to do that. So you'll have to think about your application holistically, see what operations you would need to do your task, and then make sure you put hardware for those. So that's this part. What about the output side? So there are a couple of things that we still have to do. One is we have to know whether the amount is 0. because our controller we were checking is the amount 0, and if it was 0, we were taking some action. So what we do is we put a 0 detector out here. It's equal to 0. How would you make a 0 detector? The amount, the n-bit quantity is whatever, let's say 32-bit is equal to 0. What do you think would be in this box? Yeah, but comparison by 0 is a lot simpler, right?
XOR it and then NOR it. XOR it is 0 and then NOR it.
Okay, you could do it even simpler.
You could OR them all together and then invert it.
Exactly. Okay. XOR is much more expensive. OR is a lot cheaper. Okay. So that's just an OR gate with stuff like together. Okay. So that's simple. So we need to detect 0. What else we need to do? We need to detect that another thing that you're doing is, was there enough money? Right? We were also checking for that. So I need some way of detecting that. Was there enough money? So this part is doing that. So it's basically checking whether amount is greater than equal to price. So that's a comparator. Here we do need a comparator because amount could be arbitrary and price could be arbitrary. Okay, so I do need a full-blown comparator. So I do that and I generate a signal called enough. So I have two signals, 0 or enough, and we are feeding them back out here to the controller. So this way, wherever in the controller we needed to examine, was enough money deposited, is the amount left over 0, I would be able to do that. Again, notice at this stage we are still kind of just doing this free-form design. We are making reasonable choices about the kind of things we do need to do to have to pull off our high-level strategy. We are still not done. We still need to control those mechanical parts of the machine. So there are two things that we need to do. One is to tell the machine to serve the drink, and the other is to tell the machine to serve a nickel, okay, to return. So those are our two signals: serve the drink, serve the change. Okay. Again, probably kind of the idea is we'll pulse the signal to serve a drink, pulse the change signal to serve a nickel, and as the change. And then what will happen is so the strategy would be to say, set out, release a nickel, it will release a nickel, it will tell us it released a nickel, so that we will get to the done signal, and then we are going to arrange for for 1 nickel to be detected from our amount, okay? And likewise, when the drink is served, then we are going to arrange for the price to be deducted out of our amount. Okay, so this guy, the controller, is at the heart of it. It is generating the signals to the machine. It's getting signals from the machine. It's getting signals from the data path, and it's sending signals to the data path. And it's essentially kind of a traffic cop orchestrating all these things to make sure the right sequence of stuff is going to happen. So now we have our data path, and it seems reasonable that it would be able to do what we desire, the set of operations it could do. And at this stage, one could go on to, so at this stage, one could go back to our state machine and flesh it out, okay, in terms of the specific signal names and all that we have. I'm not doing it out here, but you will so for example, while I'm in the deposit state, as these signals, nickel, dime, quarter, as these things are being received, I'll have to take different actions. So that simple abstract state machine will become more fleshed out in the process. And then finally, you will have to operate this thing. So when it comes to finite state machine and in Logisim, one key difference that will now happen is that you will be testing with a clock. There will be a clock which will be running and mimicking as if your state machine is running on every clock tick, and then you have to see whether the waveforms come out right or not. In this particular case, this is some sequence of scenario as it unfolded, and I'm just going to highlight a few key points out here. So we start out at t equal to 0. There's a reset. So this is the reset part which is happening. And when things are reset, what you see out here is at the first clock tick at which reset is noticed, see the amount is made 0. Okay, so amount is made 0 once we saw the reset, and one thing you can see is this is a more type machine that's happening. Okay, we basically are observing the input at the clock tick and setting the amount to be 0. Okay. Meanwhile, 0 went high because amount is 0. Enough went low because price is some high value. I forgot what the price was on this, but it's something. Okay, so now the amount is 0. Now what happens is on every clock tick, we are going to examine what is the status of one of the signals. Now, in this design, we are going to make the simplifying assumption in this vending machine that when a nickel is deposited, the nickel signal goes high just for one clock tick. Okay, somehow other circuitry makes that true. Okay, so what is happening is, if you see out here, the nickel went high, and as a result, our machine saw the nickel went high, and amount becomes 1. So at this stage, amount has 1 in it, which is 5 cents. Enough still remains low because we have not hit our price, but 0 becomes false because the amount the user has deposited is no more 0. Then next clock tick, we so now the dime went high, and then it went low, and okay, what is yeah, I guess there. This is making an assumption that there are faster clock ticks. So the amount goes to 3 at some intermediate clock tick which came while the dime was high. So now I have 3 out here. At some stage, now the user attempts to dispense. So user hits the dispense button, but it seems like there is not enough money in it, so nothing is dispensed. Then at some stage, a quarter is deposited, and at that stage, we have uh, amount increases at 5. Then the clock stays up, so there is another quarter being deposited, and therefore the amount goes to 13. And then finally, a dispensing is done, and after the dispensing is done, the amount goes down to 2. So the drink took away 55 cents, 11 nickels, and then finally, and see, this is where the drink was served, and then 2 nickels are released because 10 cents were remaining. So there's a sequence of things which are happening, and these are kind of the details of this particular design, but the controller is making all this sequence of stuff happening, and the data path is simply kind of executing those instructions. So a way to think about this is that the controller is like your program, and the data path is like the computer executing those instructions. Okay, and indeed, in our normal CPUs, something like that happens. Your instructions are your assembly instructions of your program basically are interpreted by the controller, and then there is a data path which can execute all those add, multiply, divide, all those kind of operations that we kind of look for. So these kind of timing flows, one are kind of in the details of it, but at the high level, this decomposition is what one has to do. So deposit nickel, deposit dime, attempt dispense, 2 quarters are deposited, a dispense is done, drink is served, return first nickel, return second nickel. That's the sequence of events that took place, and everything else is in kind of support of that. These kind of designs can get extremely detailed and messy, and so one has to kind of approach them very carefully, simulate a lot, uh, stay away from melee type designs. I know there was lots of discussion on Piazza on this issue. Melee machines can make debugging particularly tedious and hard. So just stick with things happening at clock tick. Worst case, all that is happening is you're going to be paying with a little bit more delay in the output. So now this vending machine example is complicated. We are going to work with in a design assignment. We're going to work with simpler examples. Tomorrow, both Salma and Shelly are going to go through some additional examples of this type where you have a data path and a state machine, and how do you kind of split these things. But real designs are like this. When you do the lock that I was mentioning, you are going to, well, the data path part there is probably going to be simpler, but you still have some data path out there. So you'll have to think about how to structure it. So let's look at a combination lock, which is in the vein of what you would be doing, but kind of the details are a lot different. So what we have is a decimal keypad. The user is going to, there is a key, 4-bit key, with an accompanying key valid. So there are two signals. I'm getting a 4-bit signal saying what key it is, and I'm getting a key valid signal telling me that the key is currently valid. You can look at that signal. User enters a sequence of digits and then presses enter. And kind of the idea is that this sequence, as you are pressing, you are is stored in some memory. So these keys are coming in. You're going to store it in some internal memory, and its length is available as a variable. How much has been fed in? If sequence was correct, then there is some output signal called unlock, which is going to go to the locking mechanism and it's going to unlock it. To relock, the user presses enter again. If the sequence was incorrect, a busy signal is output. So the idea is that you don't want the user to keep trying lots of passwords until he's able to break. So a busy output is asserted, a timer is activated for a predefined period of time. So there is a timer hardware out there. We're going to say start the timer and we're going to wait for the timer to be done. So when the timer is done, then the user can try again. Okay, so essentially what's happening is we enter a key, we press. If we press the wrong, if our key, code was wrong, then the lock will essentially freeze for a bit of time before it will allow us to do things again. External circuitry makes sure that key valid and enter, these signals which the user is pressing, are valid only for one clock cycle per press. So this goes to the issue that I was mentioning earlier, that when we press a key, then we are operating at human timescales. So when we press a key, it will stay, the key remains pressed for thousands and millions of cycles. So usually some extra circuitry is used to just clean it up. So we just make sure that the key is high just for one clock tick. So this is a combination lock, and again we can think in terms of dividing it into some controller part and some data path part. So let's think in terms of the high level strategy. So firstly, looking at this design spec, what do you think my data path will need to do? What kind of operations or what kind of things I will need to have in my data path? It will keep track of what?
What user?
Okay, so it has to store those numbers. So I'll need some registers to store the numbers. What else would I need? I have to compare them, right? So I need something to compare. So presumably there will be some sort of a comparator.
Counter for the time.
Okay, so I need a counter or a timer. we saw a timer circuit here earlier, so you can imagine I have that timer available. So I'll need that. I'll need a counter or a timer. I'll need some sort of a comparator. I'll need some sort of a memory to store the stuff that user fed in. I'll probably also need some sort of a memory to store the correct sequence. Okay. So that sounds a reasonable set of things. And then I'll have, what kind of signals do you think the controller will need to send to the data path? Start the timer, right? That's one thing for sure. What else? Okay. What about the other way around? What kind of thing do you think the data path will send to the controller? Okay. Correct. The correct code press. So there's a match of some sort. Okay. What else? Timer done, right? That seems like another one. So at this stage of the design, you basically will have to kind of mentally think in terms of, yep, I have a data path, I have a controller. What kind of operations do I need in the data path? What kind of signals are going to go into the data path? What kind of signals from the controller, vice versa? What are the external world signals? All those kind of things. So you'll have to kind of reason a little bit about that, and then come up with a high-level strategy. Okay. And that high-level strategy, again, remember I said assume that the data path exists. Let's first get the high-level state machine there. So this is an attempt at it. Okay. So there is an initial state, enter, where we go upon reset, and this is where the user presses the keys. So the user is pressing the keys, and we'll arrange that somehow as the user presses the keys are getting stored into a memory location, and somehow I have some sort of a comparator which is matching these things. Okay. If there is a match, so if the user presses enter, and let's see. Yeah. So if the user presses enter and there is a valid match, that we go to a state called open. We are going to unlock the lock, so we are going to send some command out to the unlocking mechanism, and then we'll go back to the enter state. If on the other hand, the user presses enters and there was no match on the key, then so there are two possible cases which may happen with the key. Okay, so key is a bunch of digits. The user may press the same number of digits and the key matches, or the user may press more digits, in which case the key certainly doesn't match, and the other is the user presses the right number of digits and the key doesn't match. The thing that we'll have to avoid is that the user just keeps typing keys until a segment just happens to match. Okay, so what this design does is it has a separate length match and a key match. So what's happening out here is that if the key is valid, if it is valid and match did not happen, then we go into some sort of a wait state, and then we let the user enter stuff. Okay, let the user enter keys until such time the user actually presses the enter. So basically, as soon as we realize that things are bad, we move to a bad state. Okay, we don't wait for the user to press the enter key. On the other hand, if the user presses the enter and there was no match, then I go to this other wait state, and we are going. This is where we'll do our timer stuff, and then when the timer says done, we come back. So this is, we are going to spend time out here waiting there. So the first wait is we have realized early that the key is bad, or whatever, what the user is pressing is bad, and we are going to just sit out there until the user hits the return. Whereas the second wait state is when now we are committed to saying, we have said, yep, the user pressed something wrong, let's do this timeout business. We are going to lock, we are going to freeze the lock for a bit using our timer and then come out of it. So that's the high level strategy. So start and enter state gets K match and L match from the data path. So K match is basically saying is it a key match, and L match is a length match. We stay in the enter state as long as the correct digits are pressed. So as the digits are coming in, we are going to keep matching them against our correct secret code. So we'll stay in the enter state. If the enter is pressed and we have the length match, and of course we have the key match because were in the enter state, then we move to open. If on the other hand, at any point in time there is a mismatch of the key, I go to wait one. And we stay put there, wait one, we stay put there, the user can keep pressing keys. At some point the user will press enter, and at that point I go to wait two. The other possibility is that the match happened, but there was no length match. So in which case I directly jump out here. So that's the second thing. Stays there until enter is pressed, wait two. And if enter is pressed, but only part of the sequence was entered, so my secret code was 4567, user pressed 45 and hit the enter. So in that case, the length match fails, so I move to wait two. So and in wait two, we start a timer. So we'll send a signal to the timer saying start, then we'll wait for the done signal. And once done comes, we come out of the wait. So that's the sequence of things. So now we can think of our data path. So what's happening is the 4-bit key, and what we'll do is every time the user presses a key, we are going to change the address in the ROM that we are looking at. So kind of the idea is in the ROM is a secret key starting from location 0. So when we start out, we are pointing to address 0 of the ROM. So when the user presses the key, we are going to match it against the first entry of the code. And that is my key match signal. Every time the user presses a key, we are going to increment a counter so that we point to the next entry in the ROM. So basically what's happening is the secret code is sitting in a ROM, which is the array. And first time around, I'm going to compare against entry number 0, next key entry number 1, next key entry number 2, so on and so forth. And as long as the match keeps happening, I'm going to stay put in the entry state. If match fails and the user hasn't pressed enter, I go to wait one. If the user presses enter and length is not a match, I go to wait two. If the user presses enter, key match had taken place and length match is also true, I go to unlock state. So that's the other thing we are doing. We know the length of the secret key, so that's somehow there, and this index is telling me how many keys the user has pressed. So I'm going to have a comparator. So this is how many users have pressed the index, and length is the actual length of my secret key. I compare and say whether there is an L match. And then finally, I have some timer someplace, part of a data path. So I basically load the timer, and then I start the timer saying start counting, and then when it is done, it sends me a done signal. So I have a timer hardware from earlier slides. So what we are doing out here is we are keeping the secret key in the ROM. So this has the secret key. Length is the length of the secret key. This index is going to tell us number of keys pressed by the user. And there is this counter, and in the counter, if you see, there is an ink which is going to increment the counter. So every time the user hits the key, the counter is incremented. So that could be done through that valid signal that we had talked about, and then the key value goes into the comparator. K match and L match are going from the data path to our controller. done is going also to the controller. The load and the T weight are the actual value of how much we want to wait. The timer value is probably a constant. Load is a signal that the controller is going to send. So these sequence, all these things as to what signals are going back and forth between the controller and data path are going to be part of your design. You have to kind of decide what signals I have to send back and forth. But that's an example of a lock. So essentially compares length and value of the code entered, and this is the timer part right there. So the design assignment would be kind of a variant of this lock, basically, but you'll be implementing it with hardware. As you practice more, again, during the discussion section, we'll expose you to more designs, and then Paul will go through another example on Tuesday. Hopefully, you'll get a better feel. But the thing, again, that I would say is really sort of these problems look very overwhelming on first attempt. Okay, there's just lots of details. So your strategy is really kind of break down the problem. First thing is think in terms of what should the data path do and what should the controller do. Assume the data path is there. First, create a high-level state machine for the controller, and then go and flesh out the data path. That's the sequence of steps to kind of take, and then you sort of create the design for both of them. If your state machine for the controller is becoming very complicated, that's usually a signature that you did not have your data path right. That is, you are carrying the burden of the data path onto the state machine. So if you are doing things like counting and all as part of the state machine, it's probably not a wise thing to do because you'll have too many states there. So use the data path for things like counting stuff, for timing stuff, for storing large values, whereas use the controller for things like making decisions and all. Okay, that's kind of the split that you have to do. So we realize this is probably the hardest part of digital design that you would see in the course because it's logically very complicated. You are essentially writing complicated programs, but you're doing it all in hardware. Okay, so hopefully through sort of sequence of examples, more examples that we'll give in the discussion section, and through the design assignment and the P-set will hopefully sort of prepare you for that. And again, those of you choose to do the design assignment number 4, you'll kind of see it in a hardware form also. So that kind of wraps up this part of the module. So this slide set. So the main things that I wanted to point out was that stateful systems or sequential systems come in these two distinct varieties: data path, state machine, and control. Data path and control FSMs. Most systems have the two tightly coupled. Sometimes you have systems which are only data path or only controllers, but usually, generally speaking, they will have both elements. Your design therefore involves splitting them and figuring out what goes where. So this partitioning is probably the hardest task that you would have to deal with. Part of the reason it is hard is that unlike what you have seen previously, where you had a set of inputs, you had a set of outputs, that's all you had to worry about. Now you have the flexibility to decide what information goes back and forth between these two things. So there's a lot more freedom, but then that creates the complexity with it. So best thing, so again, when you do the P-set also, make use of Logicin, test out your design there. Okay, that's a quick and dirty way of kind of validating things. Do the simulation, see what is happening clock tick by clock tick, in the process. One comment I wanted to make, because again I think I saw on Piazza, circuits cannot violate causality. So let me explain what I mean by that. Things happen at a clock tick, true. Namely, the clock comes at that point in time. We observe input. We do take some action on it. So oftentimes when we are looking at sort of signals and all, it would appear to you that a signal changed at the clock tick. What it is really doing is it's changing a little bit after the clock tick, right? Because when the state changes, when the clock tick comes, the state changes. In the diagram, it would appear that the state changed immediately, but it would be changing a little bit after that. And likewise, if there is an input signal coming from a previous stage, it too is changing the clock tick. So let me try to explain what I mean, so that when you do these designs, you would be okay. So let's imagine I have two digital systems. This is digital system 1 and this is digital system 2. There is a signal which is going from this to this. This guy thinks of it as the input signal. Okay, so this is the input signal, but it's being generated by another piece of digital hardware. Let's imagine that this signal is coming from a state register which is inside here. Okay. Let's further imagine that this signal goes to some combinational logic, which in turn affects the next state of this hardware. And this combinational logic probably also makes use of the current state. Okay, so that's the structure we have. So we have a signal coming from one state machine. It is feeding into a second state machine and affecting this next state. Now let's look at what will happen at the clock boundaries. Let's say our system is positive clock type system. If I monitor this in signal, then it is going to change at clock ticks, generally speaking. What I mean by that is it may not change, but if it changes on the clock tick. Agreed? Because it's coming from another register. So it might look like the following. If I observe this in signal, this guy, then it might change like this. But what is really happening out here? It is changing a little bit after this guy. There's going to be some tiny time delta. And likewise, when it changed out here, there will be some tiny time, another delta prime, let's say, that delay can change. Agreed? So even though n seems to be changing at that clock tick, it's really changing a little bit later. Now what about this guy? When would it notice that this n went high? They're operating off the same clock. Therefore, the earliest time this guy will notice, this DS2 will notice that n went high or low, would be at the next clock tick. So, so as you think about these, you'll have to think in terms of when is a signal changing. Now, so this is one design, but let's imagine there was another signal out here, which took some other bit, went through a combinational logic, and there is a second signal, and let's call it in prime. And let's say this combinational logic has a lot of delay. So if I were to look at in prime, it may change much later, because this long delay may come from this combinational logic. Okay. So when the input signal changes relative to clock tick depends upon what is happening in the logic which was previously there. All we can say is if it changes, it won't change after the clock tick, but how much after the clock tick depends. For it to be seen by this guy, it has to be seen by this clock tick, and we're going to talk more about it in the next slide. But in no case can DS2 see the changes before the next clock tick. Okay, so even a very simple design. Consider the following. Let's consider this very simple design. I'm going to call this signal A, I'm going to call this signal B, call this signal C, call this signal D. Let's say the flip-flops start out with values, let's say the value of this flip-flop was 0, this was 0, this was 0, this was 0. So what are A, B, C, D initially? They are all zeros. Let's say, so let me call this signal in. Let's say in looked like the following. And I want to draw A, B, C, and D. So what will happen on the first clock tick to A, B, C, D? Anyone wants to take a shot? So what will happen to A, B, C, D? We know nothing will happen before the first clock tick. Okay, so first clock tick, what would happen? Okay, A changes. Okay, so that makes sense. A changes. What about B, C, D? They won't change, you're saying. Why?
Because it changes after the clock tick. So
Exactly. So A changes after the clock tick. So as far as this flip-flop is concerned, at the first clock tick, A was still 0. So B, C, D will remain the way they are. Next clock tick, what would happen?
B goes to 1, A, and then the rest are all low.
A goes to low and B goes to 1 and C and D still remain 0. Okay, good. So at this clock tick, A will go to 0, B will go to 1, and these guys remain 0. And the reason is, so remember these changes are happening, so A is changing and B is changing. And the reason is, as far as this flip-flop is concerned, the second one, A is high at that clock tick, it hasn't yet gone to 0, and therefore it would capture a 1. In parallel, the first flip-flop is going to be making A 0, but both of those actions are happening after the clock tick. At the clock tick, this is switch is happening. And by the same logic, what will happen in the next clock tick? B will go down to 0, C will go to 1, and then finally at this clock tick, C will go down to 1, and D is going to go to 0. So as you analyze these circuits, bear in mind that at a flip-flop, output may be changing and the input may be changing, but there's nothing wrong with that. I mean, it's the flip-flop, as far as concerned, is handling things right at the clock tick. Okay? So some of these questions about mealy, more, and stuff like that. Okay, so the thing I wanted to point out was that while mealy kind of sounds selective, in reality, most of these signals are coming from other logic anyway. So they themselves are changing at clock ticks. So mealy is used very, very rarely, usually for in very specialized circumstances. By and large, you should just stick to more design. It is safe. It's how good, robust design is done. And independent of that, there is nothing that you can do in mealy that you cannot do in more, other than that little issue of the clock tick, clock delay. Okay. So let's see. Let's move on to the next module. So I think it's 5:23. So instead of giving a break, I'm going to just stop earlier and continue for another 10-15 minutes. Okay. So the next topic gets into these issues of timing, and how things play out when we worry about the circuit details as well. Okay, so this is chapter 15. Okay, so what the question we are going to now seek is the following: how fast can we run a circuit? Okay, what are the limitations? So thus far we were, although I talked about delays and all, but we were really not sort of, we were just assuming that things somehow work correctly. What we'll see in this lecture is the following: that well, we'll see it next time, but I'll just start on the story. That there are circumstances under which your circuit may fail if the delays are not correct. For example, intuitively, if my combinational delays are too large, then my next state may not be ready before the next clock tick, and then things can start going bad. So to be able to understand this, we also have to have a very well-defined notion of what clock timing that we are talking about. There are basically two types of questions that we would like to answer. Number one, how fast can the design be? And number two, will the design work correctly? That is, will there be any failure of timing? And we'll see that there are two ways we can fail. One is we are too slow, and the other is we are too fast. Both ways can result in failure. So I'm too slow, therefore and clock is too fast. And the other is I'm too fast, and that leads to what are called as race conditions. There are softer analogs of it, but that you see the same kind of thing, like two programs trying to do something together, and one may move too fast or too slow, and that can cause problems. Similar kind of things that happen out here. So digital design, as we saw, is driven by clocks, and clocks have periods, and there is a pulse width of the clock. There are several styles of implementing circuits. The one I have been assuming thus far is one where we say, the pulse width doesn't really matter. All we care about is the period of the clock. There are ways of implementing digital logic where the pulse width also matters. There are also digital systems which are called as multi-chronos systems. Multi-chronos, chronos is time, multi-chronos means multiple clocks. So instead of having a single clock, they may have multiple clocks which are synchronized to each other, and then they're aligned, like one is a multiple of another, but different parts of the system are operating at different rates. Again, we'll not worry about those. So what we have is a single clock operating at some rate, and we don't care about this pulse rate, we'll only care about the period. So the question we want to answer is that given if I have a circuit that we have implemented using real D flip-flops and combinational logic, will it work in any will it work at any speed, or when would it fail? At what clock speeds would I run into problems? So let's go back to our sort of generic view of a sequential system. So I have some sort of a state register. The state register is updated by a clock tick. I'm calling it a state register, but it may really be multiple registers scattered all over my design, but collectively we think of them as a state register. I have a combination logic, in, out, so the usual stuff. At the clock tick, the state register reads in the new value, and that becomes, so that reads in the next state, and that becomes a new current state at the clock edge. So this is a version of the similar timing diagram as I was showing a short while ago. So what I have now is a state register. I have a mux that it has two inputs, possible inputs, either a 0 or a +1. Okay, so under normal mode, for example, if I'm not resetting it, then it will just increment the count. So count will become count +1 and count +2, so it will keep incrementing it. So if I look under the hood, what would be happening out here, if I kind of look out here, then the clock, at the clock tick, what would happen is that the new value, the register will get a new value. So the count will change after a little bit. So whatever was on next will become the new count at this. So there will be a little bit of delay, which is because of the delay in the D flip-flop. So it is this delay. So this delay is because of the delay through the D flip-flop. So what I mean by that is when the clock tick happens, the D flip-flop reads the value at its input, and that becomes the new content of the flip-flop. It will appear on the output, not instantaneously, but a little bit after the clock tick. And that you can think of as the delay through the D flip-flop. Then, once it appears at the output of the flip-flop, namely at this point, then it will go through our incrementer, go through the multiplexer, and become available as the next value. And that will take some time. That time will depend upon the delay through the incrementer, delay through the mux, and the delay in the wiring. So the second unit of delay corresponds to all that combinational and wiring delay that we talked about, that I mentioned. And therefore, what would happen is that if I look at next, I will see the value 2 on it, some delay after the clock tick. So from the clock tick to this point, this delay is going to be the sum total of flip-flop and all the combination logic. And then at the next clock tick, this next will become the new count. And that process will repeat itself. So, yeah.
Why don't we even bother representing clocks as just kind of square pattern? Why aren't they just impulses? Because we're only ever, at least when we're inducted to everyone.
For the kind of clock we are discussing, we can do that. Sure. The only reason it's not done is because the tools which are used to visualize, they always think in terms of 0 and 1, and also because the clock in reality is a 0-1 signal which looks like that. Okay, but in terms of reasoning about it, you're absolutely right. It won't matter because as far we are only making use of its pulse property for the kind of design we are doing. There do exist, as I mentioned, other ways of doing circuits where the level also matters. Okay, the book has some discussion on it. I will not go into that. So there are styles of flip-flops where the level also matters. Okay. So looking at this, what can you tell me about acceptable delays of flip-flop and combination logic for the circuit to work correctly?
That's the combined has to be less than the clock period.
Exactly, right? So if flip-flop plus combinational logic plus wiring delays, if it is more than the period of my clock, then this new value of 2 will not be ready in time for this clock tick. Okay, and we'll see there are some additional details which come in, but to the first order, that's the right thing to have that. My delays cannot be too large because if they're too large, I will have a problem. Okay, we'll see that there are some other factors which can also create problems if my delay is too small, and that has to do with the fact that we are making one assumption thus far, that my clock reaches all flip-flops at the same time. In reality, that doesn't happen because clock goes over wires. So one flip-flop may see the clock coming in sooner than the flip-flop at the next stage. And that can cause problems also. So what I'm going to do is I'm going to stop at this stage and we're going to pick up these nuances and all, but we'll do it on Thursday. Because Tuesday, again, remember, is the lecture by Salma and Paul. Do not miss it because we will not be able to record it. Okay, so I want to emphasize that. That's one lecture where we cannot